Okay. Our next speaker is Paul Gavrikov from Offenburg University, and he's going to present his work entitled Insights from Learned Filters on Vision CNNs. Welcome, Paul.
All right. Thank you very much for the introduction. It's a great honor to be here. And this talk will be a little bit more analytical and motivated. I want to give you the same motivation that my PhD supervisor gave me roughly 2 years ago. And as you probably all are aware, CNNs typically need a ton of images to learn meaningful representations. And a common approach to tackle this is, if you don't have enough data, is to pre-train on some kind of other image data sets and then fine-tune the model on your actual data set. And surprisingly, it often also works when you pre-train on data that looks nothing like your final data set. So in this case, for example, natural images, and then fine-tune on X-ray. It doesn't always work, but surprisingly often it does. And the question we asked ourselves is, how can that be? And are there any similarities in the CNNs? And we proposed to study that in the learned filters of those CNNs. So my talk will be mainly based on our CVPR oral last year, which was entitled CNN Filter DB. And there we did a mass evaluation of filters that are learned in CNNs. So we basically went ahead and downloaded every pre-trained CNN that we could find on the internet. We got roughly 650 of those. And we limited ourselves on 2D CNNs that contain kernels with size 3 times 3, or mostly 3 times 3. And we tried to be collecting as diverse as possible models. So we have a bunch of different network architectures. And these CNNs were trained for all sorts of tasks. So these are classification models, segmentation models, but also generative tasks. And we also made sure that they are trained on as many different data sets as possible from all sorts of visual domains. So we have models that were trained on natural data sets, but also medical ones or thermal data sets, among others. And in total, we extracted 1.4 billion annotated filters from these models that we're now going to analyze. So the first question you may ask yourself is, how can you analyze filters between various CNNs? They might have a different number of those. They will certainly have different parameter sizes. So we propose the following method. You take a bunch of filters, you normalize them by the magnitude, and then you do a singular value decomposition or a principal component analysis. And this gives you two things. This gives you a basis which describes the patterns that are inherent in those filters. And it gives you a set of coefficients that describe the weighting of every pattern. And so what we first did is we split our filters by different groups. We were trying to be as creative as possible and computed the basis for all of them. And it turns out, here are some examples, it turns out that for all of them, we see that the basis is strikingly similar. You sometimes see that the vectors are out of order because they're sorted by variance, and they're sometimes inverted. But generally, the patterns that the basis spans is highly similar, independent of how we tried to split all filters. And that was very surprising, because this means that all the CNNs effectively sample from the same basis. The second thing we tried to understand is, how are these patterns distributed? And here we did a slightly different approach. We transformed all the filters to one common basis. Then we tried to split it, and then we get these nice distributions that you can see for every coefficient, and then we can just go ahead and do a pairwise divergence of those and then sum it up. So basically, for example, based on Kullback-Leibler. And the first observation that we had was not very surprisingly. So if I take two models, for example, a VGG-based model, and I compare it to a ResNet model, then that will learn different filters. No surprise here. But it gets more interesting when we start comparing models that are of the same family. So something like a ResNet 50 and a ResNet 101. A ResNet 101 is double the size of a ResNet 50, but it primarily is the same architecture. And there we see that the learned filter distribution is highly similar. And it gets even more crazier. If we start analyzing models that are trained for different tasks, so for example, classification versus segmentation, or trained on different data sets, for example, medical models versus models that were trained on ImageNet, we see also that the filter distribution is highly similar. So it appears that independent of what you train on, your CNNs have a very high shared similarity in internal representations. And you might also commonly have heard that representations in CNN kind of get richer and richer towards the end of the model, but this is not visible in filters at all. So distributions of filters in the initial layers are very similar to distributions of filters in the end of your model. You may now look at these two distributions and say, okay, but they look nothing alike. And there is actually a phenomenon that explains this, and we call this degenerated filters. We have primarily observed them in medical models. And just to give you an example of what they look like, here is a ResNet 18 that was trained on Cypher 10. And every row in this image represents one convolution layer on the first 30 kernels or so. And what you can see is that in the first 2/3 of the model, the filter patterns are very diverse, they're very vibrant. The model learns a lot of different transformations there. But towards the end of the model, you'll see that filters are becoming increasingly sparse. And this image is actually with increased contrast, otherwise you wouldn't even see them. And that means that these filters no longer process information, they actually eliminate it, which is probably not something that you want. The other thing that you may see is that patterns are becoming increasingly repetitive. They're just differently scaled. And that's, again, it's kind of a redundant computation of inputs, so that's also something you want to avoid. And we primarily saw this whenever models are over-parameterized, so you have a huge model that you train on a small data set. So we actually try to follow up what the difference is in medical imaging. Why are these causing so many degenerated filters? And the good news first is that medical imaging per se does not learn different filters. It was just related to our analysis, which was based on public models. So we had to take what we can. And it turns out that in our analysis, we had models that were very specific architectures, so multiple autoencoders stacked together. And there we commonly saw in one architecture that it learns binary filters. So this is something that I've never seen before. It's basically a layer of convolution filters that only have two weights. And it's not by design. This is something that the CNN implicitly has learned. And this kind of explains these weird spikes in the distributions. The other thing that we commonly saw is that models are over-parameterized. So in some cases, we had, for example, segmentation models that were 99% sparse. That means 99% of your network are not doing anything. In this case, we couldn't verify if the model was actually working. It might have been that it learned some kind of weird shortcut, which the authors didn't intend to. So I want to encourage you, if you experience something like this in your models, go ahead and exploit this by design. If you see that your model is increasingly sparse, then reconsider using a smaller model. And if you see that it's learning some kind of weird filter distribution, try to reformulate your search space such that you can exploit this and train your models faster and probably with less data. So at this point, I want to make a cut here with that analysis and shift to a different topic, which is adversarial robustness. It's also becoming increasingly important in the machine learning community, and I guess most of you are familiar with that, but just for those who aren't, CNNs and all kinds of deep learning models are very vulnerable to small shifts to the input data. So, for example, here you have a mole that is correctly classified as benign, but if you add this little noise pattern, you can actually fool your model into making a wrong prediction. And not only that, it makes a wrong prediction with very high confidence. And unfortunately, when you train your models in a standard way, you're very likely to train models that are highly vulnerable to this. A common solution to this is adversarial training. It has a lot of problems. It's only a partial solution, but let's assume for today that it's a good option. And we asked ourselves, what happens if we do adversarial training? What shifts do we see in the filter patterns? And there are three things that you can see. So we studied this on 3 different data sets, Cypher 10, Cypher 100, and ImageNet, which are all classification data sets. And we asked where the differences are in the models. So we trained models with adversarial training and without and compared them. And you can see 3 things. The first thing is right in the beginning, the very first layer, there are differences. and then gradually it increases towards the end. And the third thing that you can see is that it's highly dependent on the data set. So for Cypher 10, you see a large difference. For Cypher 100, which is a bit more challenging, it starts to decrease, and in ImageNet there are barely any differences. So you can actually conclude that adversarial training kind of helps with this overparameterization and kind of injects synthetic data that leads to less degenerated filters. And you can also see this if you look at the filters. At the very end, you'll see if you do standard training that your filters are again degenerated, the patterns are very repetitive. And instead in robust models, you see that they're different and diverse, which is what you want. It gets more interesting in the very first layer because this is something that CNNs have learned to do. And on a standard model, you see all kinds of filters that you would expect, so color blobs, Gabor filters, and the likes. But adversarially robust models learn a very interesting filter, namely only one that has the center weight activated and all the other weights are 0. And it has a very special function. It can, in combination with the activation function, actually eliminate a little bit of that adversarial perturbation. And this is not something that you do explicitly by design. This is something that CNNs learn implicitly. And importantly, we saw this in all the models that we have analyzed. So it's quite interesting that CNNs kind of learn this weird pre-processing step where they're able to clip away a little bit of noise. It doesn't solve adversarial robustness completely, but it's a nice, helpful tool that CNNs learn. And so to wrap this talk up, we have seen that filter distributions are very similar, independent of what you train on, which was a quite interesting observation for us, also independent of the task or the depth in the model. And this means that the way we currently initialize CNNs, which are completely independent of each other, is not optimal. There must be a better way to initialize CNNs, and this is something that we're currently working on. And it also means that in terms of filter distributions at least, pre-training with any kind of images should work as long as you have enough image data and you have complex enough image data. Whatever that means is probably defined by your actual problem. The second thing we have seen is that adversarial training has a regularization effect on filter patterns. It kind of bridges the gap to simply using more complex data sets or more data overall, and it learns a very distinct filter. And lastly, I hope this talk motivated you to analyze your CNNs and the filters that they learned, because this can help you to understand overfitting in your models and also overparameterization. Based on this, you can optimize your network, and you can also probably select better pre-trained models. This is also something that we're currently working on. The working hypothesis here is that models that have degenerated filters probably won't transfer very well. So lastly, I want to say our entire code base and the entire data set with all the 1.3 billion filters is available on GitHub, so you can download it from there. And we also have 2 PyTorch libraries that you can use. One is Torch ConvView, which allows you to visualize your CNNs. And the other one is Torch Conv Quality, which is actually a metric that we have developed to quantify the quality of your CNN filters. And you're welcome to download them and use them. And if you want to contribute on GitHub, you're very welcome. Thank you very much.
Thank you, Paul.